We learned in a previous video that the op-amp's inverting input terminal provides a convenient means of implementing negative feedback. However, we can also use this terminal to create an amplifier that simultaneously amplifies and inverts the input signal. Inversion corresponds to a negative closed-loop gain. For example, GCL equals negative 10. Since Vout equals Vin times GCL, a negative gain will cause a positive input voltage to become a negative output voltage, and vice versa. With sinusoidal signals, inversion can be described in terms of phase shift, and inverting a sinusoid effectively creates 180 degrees of phase shift. Why would we want to modify the signal's polarity? In some cases, inversion itself is desirable to change negative inputs to positive voltages. In other cases, inversion is not required, but it is also not problematic, and we use the inverting amplifier because it offers performance or functionality that is not available from the non-inverting amplifier. For example, the inverting configuration can reduce signal distortion, and it allows you to attenuate a signal, which isn't possible with the non-inverting configuration. We can use standard circuit analysis techniques to determine the relationship between the input voltage and the output voltage of an op-amp inverting amplifier. The non-inverting input terminal is connected directly to ground. This means that we have 0 volts at the non-inverting terminal and at the inverting terminal by assuming a virtual short between the two. Vin is applied to R1 and generates a current of Vin over R1 flowing toward the inverting input terminal. Since we assume that current cannot flow into the input terminal, all that current flows to the output node through R2. The voltage drop across R2 will be Vin times R2 over R1. The left side of R2 is at 0 volts, and since current is flowing from left to right, the voltage on the right side of R2 must be lower than the voltage on the left side. Thus, the voltage at the output node will be 0 volts minus the voltage drop across R2. In other words, Vout equals 0 minus Vin times R2 over R1. Based on this analysis, we can express the closed-loop gain, or GCL, of the inverting configuration as negative R2 over R1. Note that this differs from GCL of the non-inverting configuration in two ways. First, the negative sign means the gain is always negative because the ratio of the two resistances will always be positive. Second, GCL for the inverting expression does not have the 1 plus term of the non-inverting configuration, indicating that the gain can be less than unity. For more details, check out the link in the description or visit allaboutscircuits.com.